Okay, done. You can record this class. So this this equation can change into. But I think this equation you get will have mi. You're welcome. AI sigma mi. So actually, it is the same because we can times rho and L for each mi. So this equation will change into this. So we also can change this equation into this. So this letter M means the total mass of all the system of particles. No, so this is very important concept. So actually, when we are really use this, we always do the projection this vector equation into three axes. So maybe we will often use xc equal sigma mi xi, you know, sigma mi, and yc equal sigma mi yi sigma mi. So because almost all the problems we are going to tackle will be plane, in the plane system, 平面系统, right? So we will always use this equation, 平面系统. So that is the center of mass. How to calculate the center of mass of a system particles. Maybe you guys think about why we talk about this, why we should use this equation, because we have learned the dynamics of a particle, right? We talk about the second law of Newton's, F equal ma, right? For one particle, because the rigid body are a system of particles, we are going to talk about its acceleration of its center of mass. Then, if we have this, we can do 1 second, two calculations. So we will know xc 2 dot equal acx, right? Equal this sigma mi xi double dot sigma mi. And this will be sigma fx. So we can have this relationship between forces and accelerations. So acceleration, we can think about it kind of kinematic information, right? Actually, we have learned a lot of measures how to calculate velocity and acceleration from the middle part of this course, right? And from the same reason, we also can have yc double dot equal acy, right? It should equal mi sigma mi yi double dot sigma mi, and then equal sigma y, right? So actually, that's the whole theorem momentum of this chapter's caption, So we call that theorem of momentum. We Chinese call that 动量定理, right? So 动量定理 actually tell us how to relate. Actually, its expression will be dp dt equal equal sigma f. So that's the all the theorem of momentum all about. So maybe we will talk about what is momentum and what is impulse from the sections. So the first section we talk about the center of mass of a system of particles, just to prepare for the theorem of momentum. So let's see. So that's all for this, and that's why we use this equation. We introduce this equation again, and I will use the other thing I have right on the screen. So you guys can think actually if we have a fixed coordinate system, so if this C means or denotes the center of mass of this system of particles, so we can draw a line from O to C. So this vector OC will equal RC. It will mean the position of this center of mass. So if this system of particles will move in some patterns from one position to another position, so you guys can find actually this RC will be changed at different time moments, right? So that's why we have to learn this equation first, and we can use the vector expressions to write its three components along three axes. So actually RC can write as equal XCI, right? Plus YCG and plus ZCK. So we got its three projections onto three axes respectively. So we have this and this. I have write these two equations here before, and this we will not often use that. But if we encounter the space problem, maybe we should use this. But almost all the problems we are going to tackle, just use this 1-2 expression is enough, right? So that's the center of mass of a system. Let's continue. Let's talk about the external forces and the internal forces of a system of particles. This is important, so we better learn that and understand that. So external forces are the forces exerted on the members of a system. So here, members maybe it's just a body system. So maybe I can draw you guess a body system or making them. So we always do this kind of crank and slider mechanism. Do you guys still remember? So we have this. I'm sorry, it's not good enough. Maybe I should change it a little bit. I'm sorry, so I will try to draw it again. Let's say we have this kind of mechanism, and this is the slider's horizontal trajectory, and we have the so this A, B, and C. See, we always draw making them like this, so we know actually we can call that AB is a crank, right? Because it can rotate around point A with 360 degrees. So actually, it is a rotation around the fixed point or axis, right? One of the simple motion of a raised body. And the slider C, AB, and this C slider, actually it will always along the horizontal trajectory to move left and right, right? So actually its motion is translational motion, which is very simple. Translational motion, right? Another is this BC. So we call that link BC. So we always said actually at point B, link BC connected by AB, right? And at point C, link BC are also connected by another constraint at point C. So actually it have a complicated motion that is plane motion, right? Plane. We have learned how to find its kinematic information, right? So here, back to this, because the third part we are going to learn the dynamics of a system, right? So here inside the external forces are forces exerted on the members. Let's say YAB can rotate around A with this CCW direction. Maybe there is a moment, right? Moment. So maybe this ladder will move from right to right, from right to left. Maybe there will be a force. Which is a constant vector, do not change its magnitude and direction at different time moments. So this M are exerting on the member AB, and this F are exerting on the slider C. So we call these kind of forces are what? External forces. So that is external forces are the forces exerted on the members of a system by particles or bodies not belonging to the given system, right? So actually, maybe there is another object which exert this moment or this force onto this AB or this letter C, but this object do not belong to this mechanism or body system. You know, so that is external forces. When we talk about internal forces, are the forces of interaction between the members of the same system. So maybe if we call there a lot of particles which are constituted, which constitute a system of particles. So let's say this particle 1, this particle 2, because some of the reason maybe it will attraction each other, right? Attraction each other. So we call that is F F21. That is a attraction force by particle 2 to 1, and this is F12. So this kind of internal forces, it happened between two particles on the same system. Or maybe we can think about this constraint B. So if we select AB as the object to be studied, so because the type of constraint, so there will be FBY and FBX, right? And here we'll have FAX and FAY. And if we select BC as another object to be studied, then we know actually this is point B, this also is point B. So we will have FBX prime and FBY prime. So do you guys still remember that we have learned the so-called action and reaction forces? So this FBY and FBY prime actually is a pair of action and reaction forces. The same is the FBX and FBX prime, right? Also is a pair of action and reaction forces. So all these forces are internal forces. No, are internal forces. All this FBY, FBX, and FBY prime and BX. But this FAY, this FAX, because it is ground exerting the force onto this. So we never call this is internal forces. But this, and this are internal forces. So that is internal forces are the forces of interaction between the members of the same system, right? But as far as the whole system of the particle is concerned, so the geometrical sum, the principal vector. So at the first part of this course, we have learned how to simplify a force system, right? So we have principal vector. We also have a principal moment. Do you guys still remember? Of all the internal forces of a series system is 0. Why? Because all the internal forces are a pair. So each pair of internal forces will be action and reaction forces because they always have the same magnitudes, collinear and opposite direction. So its geometrical sum will always be zero, right? So the sum of the moments, the principal moments of all the internal forces of a system with respect to any center of axis is also zero, right? Is also zero. So we have four system of particles. Of the internal forces, its geometrical sum will be zero. Of the internal forces, its moment to a given point, its sum will be zero. Of the internal forces, its moment to a given axis, its sum also be a zero. So if you pick one internal force, you can definitely find another internal force which can constitute a pair of action and reaction forces to this the first pick out internal force. That's why all this sum will be zero. See, so the external forces and the internal forces is a very important concept. You guys should know that. Because of this, we can denote some simple expression to help us to do some force analysis to give the real relationship between the force and kinematic information, right? So that's this external forces and internal forces. Let's continue. And let's see. Then we are going to move to the second section, talk about momentum and impulse. So first we'll talk about momentum. In Chinese we call that 动量. 动 means 运动，动力学。动 means move, move. 动力学. So here we call that 动量. So move, moving or move, right? 动量, momentum. So let's see what is momentum for a particle. So there is the logic. You guys should always logical path, I think. So almost throughout the whole part of this dynamics, you guys will find we always along this logical path. First, we will give some concept about maybe momentum, maybe impulse to just one particle, to or just one particle. Then we are using this to consider a system of particles, system of particles. Because all the theorem for a single particle is very simple. It's just another expression of second law of Newton's, right? But when we take a lot of particles to constitute a system of particles, then we will find some new conclusion, and which can help us to do the first analysis of body system. Then when we finish this system of particles, we will find actually two. So one is the one body. Because through our whole course, we always treat body as a rigid body. So we can think about a single body actually is a special case of system of particles. And we also have body system, body system. So actually, when we talk about the body system, means mechanism, which is constituted by a lot of bodies, just like what we have. I have drawn a crank slider mechanism at the last page. We have rank AB, we have link BC, we have slider C, right? So that is kind of mechanism. We also can treat as the body system. So you will find all the theorem we denote from one particle to the system of particles can be applied into one single body or a body system. And this is the final goal of our dynamics. We are going to try to find the relationship between forces and information of kinematics, right? So when I introduce all this concept to you guys, you can think about this logical path. So first, we are talking about the momentum of a particle. We are talking about 一个质点的动量。So the product of the mass of a particle and its velocity is called the momentum of a particle. So it is a time-dependent vector with the same direction as the velocity, the units of which is because these kilograms are the units of mass, right? And this meters per second is velocity. So you guess that's fine. That's fine. Okay. So you guess we should always pay attention to one thing is here we are talking about the velocity almost means what? Absolute velocity. That means its velocity relative to stationary coordinate system, right? So you always should pay attention to this. Here we are talking about the concept of momentum of a particle. It is the product of the mass of a particle. We use mi to denote a mass, the mass of a particle, and its absolute velocity, right? So because this velocity is a vector, and so this momentum also is vector. So I'm very curiosity about this fact. Why we not use the first letter M to denote what is the moment of a particle? I think because we also have a mass. So if we write like this, maybe a little bit weird. So that's why we use this letter P to denote momentum of a particle, right? So maybe we should use this pi. Means we are talking about the S particle of a system. Its momentum, we just use like that pi equal mi vi. So because at the scope of our course, we think that mass and time will never change at our engineering environment. We do not think about the how to say reality of Einstein. I think it's not 相对论 or 量子力学. Here, we do not consider that. We always think time and mass will never change at our body system, just like we always treat body as real body, right? So momentum is a physical quantity measuring the intensity of a mechanical motion, you know? So what is mechanical motion? So it's a lot of motion just happened on our daily life. Maybe the velocity of an airplane, of a car, of some machine, right? Actually, the value is more is less than the velocity of light, you know? Uh less than the velocity of light. We always use c to denote because I think it's 3 times 10 to the 8th power meters per second of light, right? It very fast. But our but our mechanical motion its velocity is quite less than the speed of light, right? So we call that we just use the momentum to measuring the intensity of a mechanical motion of a material body. So this material, different material body will have different density. So its rho will be different and times volume will be its mass, right? So for example, the velocity of a bullet, bullet is very small metal object. It pushed by some kind of gun. Do you know gun? We try to call that 枪, maybe a pistol, maybe because there are a lot of types of gun, right? So its mass is very small, but it have a high velocity. A common bullet from a gun, maybe its speed maybe like 800 meters per second. Although it's far less than the speed of light, but it's quick enough for us. So its momentum just maybe equal m_v. Also, it very big. In a big quantity, right? In the case of a boat, it's just opposite. Why? When we talk about a boat, it has very big mass and very small velocity, right? Although its velocity is very small, but it has a very heavy weight, so its mass is big enough. So this is kind of physical quantity. Also, its products is very big. So if we have a river and you are going to stop your big ship, right? Just along one shore, maybe. So although its velocity is small enough, but its mass is bigger enough, so you should tackle this very carefully. Otherwise, maybe your boat will be heavily wrecked by heat. It should be highly carefully treated, right? So that is momentum. Momentum maybe means a potential of movement, right? So in some political articles, we'll see our country have a good momentum. Means economical development is quite well, right? So it show or indicate some potential, right? Maybe this also indicates some energy, some energy. So that is the concept of momentum of particle. It's very easy. It's expression just mass, the products between mass and velocity. The only thing you guys should pay attention to is here, when we talk about the velocity, always means absolute velocity, right? So let's continue. The second, the momentum of a system of particle. You guys still remember the logical path I just mentioned the last page. So first we talk about the momentum of a particle, then we immediately change to this topic, the momentum of a system of particle. A system of particles in Chinese, we will call that 质点系. So here 质点 means a particle, a particle, a particle, a particle. We call that a 质点. So maybe it means a point which has mass, right? A point which has some mass. So That means 质点. So I think in Chinese it's quite simple to express this a system of particles. So in English we have to use a system of particles, but in Chinese we only use this 质点系. That means a lot of particles constitute a system. That is the 质点系. That it is a system of particles. So the momentum of a system of particles is defined as a vector equal to the geometric sum, of the momentum, maybe the Floer 复数, right? Of all the particles, momentum of all the particles of the system. So actually it is. So maybe I can write it again. We have P means the momentum of a system of particles is equal sigma pi, which equals sigma mi vi. So maybe we give this to denote that this one, and this one also is a vector. So we can try to simplify this expression. So we know that actually P equals sigma mi vi from the knowledge point we have learned. So each absolute velocity will equal dri dt, right? So because the mass will never change at different time moments, so we can change this sequence of its calculation. So we can use this. Maybe you guys don't understand. Maybe I can give you a very simple example to let's say we only have two particles in a very simple system of particles. So we have F1 V1, right? We have F second V second. So here the momentum of this system equal this. So sigma mi vi. So we can just write as M1. So V1 we can write dr1 dt, right? Plus M second dr second dt. So because this M1 and M second will never change, so we can write as this. This can be d, the M1 R1 dt plus d M second R second dt. So you guys can do this calculation. It's the same result of this. So if we change the sequence of the calculation, so it will change into D M I R I, right? dt. So that's why we can change this into this, just because all the masses of the particles will never change. So we can change its sequence of calculation. So we can write like this. Why we should do this change? Because we are going to use this equation. Do you guys still remember? Actually, we talk about this equation from the first section of this chapter. So the center of mass of a system of particles, we have this. So we can use this. Actually, sigma mi also equal rc times m. So that means we find a very simple expression that this m denotes the whole mass, the total mass of this system of particles. And Vc is the center's velocity, the momentum of system is equal to the product of the mass of the whole system and the velocity of its center of mass. Its center of mass, we call that 质心. You see, so Chinese is more useful because we have 字典, means a particle. We have 字典系 means a system of particles. We also have 质心 means it's center of mass. So if we always use Chinese, it's quite simple, right? Maybe Chinese letter, Chinese character will have more information than a single English word, I think. So once again, the momentum of a system is equal to the product of the mass of the whole system and the velocity of its center of mass, right? So once again, we should pay attention to one thing is here the velocity of its center of mass also means absolute velocity. Always use absolute velocity because we have VA equal VE plus VR. We have learned that. So there are different kind of velocity. We have absolute velocity, we have transport velocity, we have relative velocity, right? You should pay attention to here. We always use absolute velocity. So from this definition, actually it is logical denote this result. So we can simple use this result to find some body system or some body its momentum, right? So let's see. In terms of projections on Cartesian axis, right? So because P is the vector is equal M, the total mass of the system, and VC. So we can do these projections. So we have Px equal MVCx also equal MXC dot, right? And do you guys still remember what XC, how to find XC? Actually, sigma MI, XI, sigma MI, right? So for the first same reason, we have YC equals sigma MI, sigma MI. So when we try to do this calculate, so here one dot, here should one dot. Here one dot, here should one dot, because mass, all the mass will never change at different time moment. So it's just a coefficient, right? So let's further talk about momentum of system of rigid bodies. So rigid bodies. So assume that the mass and the velocity of center of mass of the S rigid body from a body system. And MyVCI for the whole system, we get them actually. So from a body system, we also have this. And each VCI means some, maybe some rigid body from this rigid bodies, we can find its center of mass. We also can find its absolute velocity of its center mass. Then we will have this S-rigid body, its momentum. Then the total system is momentum will just equal this, right? So I hope you guys can understand this except because it's very important. We will use this, and when we talk about the theorem of momentum, we will use this. So the first thing we should know how to calculate some momentum of body system, right? So let's say a example. It's very funny. It's more like what I have drawn this picture on the previous pages, maybe just in this position, right? So in the mechanism shown in the figure, OA rotates with the constant angular velocity omega, right? With the CCW direction. We assume that we suppose that OA equal L and AB also equal L. The rod OA and AB are homogeneous of mass. 均匀的 right? 均匀的 that means OA equal L and OA had mass M. AB equal L also had mass M, right? The mass of the sled block, we also can call that a slider at B, also is M. And here, this green slide blocks is center of mass is here, right? And the center of mass of OA will be half length of here and half length of AB here is the center of AB, center of mass of AB, right? So let us determine the momentum of the system when phi equal 45, right? When phi equal 45. So I think maybe there are two methods to finish this text. The first, we can use the expression to find what? To find its the whole. So let me construct a coordinate system, right? So let's see, we just try to use this RC equal sigma mi ri sigma mi, right? So maybe we just use this xc equal sigma mi xi sigma mi and yc equal sigma mi yi and sigma mi. It's very useful for us. So let's say our m1 equal m, and it's r1 is x1. Let's say this is 1 and this is second and this third. So m1 equal m, x1 will equal what? So here so this will be half L times cosine phi, right? And m second equal m, and x second will be here. So its length on the horizontal axis will be equal L cosine phi plus another half L cosine phi, because this OA equals this AB, right? And it also tells this 45, so this also should be 45, and here should be 90 degrees. So that means OA perpendicular to AB, right? And our M third equal M, and X third will, so just 2L cosine phi, right? So from this, we can find XC and YC respectively. So let's see, maybe we just do this XC will equal, because I'll have the same. So here will be a half 3/2L cosine phi, right? So sigma mi will be m1, thank you, m1 plus m second. So here will be 3m, and here should be what should be this times m times m. So we have m plus this plus this cosine phi, right? And then we can eliminate this m and this m, and this a half also third, right? At 2, so should be cosine phi, because here we have this is constant angular velocity omega, so phi equal omega t. So we can write as cosine omega t, right? So this is, let's see the answer of this page. I just here is all I have right here. So let's see the solution. So here they're talking about the second the second method, maybe we will talk about at last class today. So here we have xc equal, I think, L cosine omega t. So you guys can find actual xc dot, right? Equal minus 3 for L sine omega t times omega. So we will have px will equal, because the whole mass will be 3m, right? Times xc dot, so which will be this. We also can find py, just need your yc. Maybe you guys can do this calculation by yourself after our class. So I think it's time for us have a short break. We will restart at 11:10, right? So all you guys please have a short break. Okay, and let's continue. So actually, I just introduced the first second is we can try to use the expression find xc and yc respectively, and just to do the one other derivative calculation, we can find the velocity vcx, right? Like this, and we also can find vcy. Then where px and py can be used the conception of this to find. And here we are going to talk about the second method. So let's see how to do this. So the second method is more like this because it is the mechanism, right? We have OA, AB, and the slider block C. We have three members, right? Actually, the fourth member is the ground earth of the frame because it never changed its position, its velocity always zero, so its momentum also will always be zero. So if because it's very easy to find each body's center, here C1 and here C2 and here C3. So then we have to find, we try to find its absolute velocity VC1, VC2, and VC3. So let's use this. So let's see. Because this rod OA, we can find actually it has what have rotation around the fixed point O or axis O, right? So its center VC1 is velocity. It's quite easy to find. Maybe I can write it here. So can you guys remember actually we learn how to do this. So VC1 will equal omega times half L, right? And how can we find this VC3? So because AB, AB actually it has plane motion. So since OA equal AB and here 45, here 45, so this is perpendicular. So we know because OA have a uniform angular velocity omega and CCW direction, so VA will definitely on this direction, right? And because the horizontal slot here, although we don't know its magnitude of VC3, but its direction should be this. So here, AB is the member which has plane motion, and we know 2 points on this body, A and B, is velocity's direction. So we can use this method to find its instantaneous center of velocity. Do you guys still remember? We call that 瞬心. Instantaneous center of velocity, because at this time moment, we can think about that it's more like this, all the points on the AB, although it has a plane motion, but at this time we can think that actually VA will equal omega AB times LPA if we use this P to denote this instantaneous center of velocity. Do you guys still remember? And VB also equal omega AB times LPB. Actually, VA it should equal omega AB times LPA. It also equal what? Omega times L, because point A also is the point on the crank OA. Right? So actually we can use this relationship to find omega AB. So let's see what the length of LPA, because here's 90°, here also is 90°, and here 45, so here is 45. Then here also should be 45. That means LPA will equal L. That means what? That means omega AB will just equal omega. And LPB. So here is L, here's another L. So LPB will equal square root 2L. Right? So we can use this expression, we can find here VB actually the VC3. It's the same, right? It's the same. Why? Because this green letter block has a translational motion. When a rigid body has a translational motion, each point on the same body will always have the same velocity and the same acceleration. Do you guys still remember? So actually our VC third equal VB equal omega AB, which is omega times LPB, which is square root 2L. So which is omega L, right? So the last one is this VC second. We should try to find the length of this. Can you guys have a good method of this? So because this is the center, this is center, and this center, and how should we find the length of PC2? How can we find its length? So here, you know, because here, let's say AC2 is half L, right? And here AP also L. So we can use, actually, maybe I can write here, PC should equal square root PA squared plus AC2 squared, right? LPA LAC2. So it should equal, so PA L squared, and this one will be a quarter L squared. Then we can find, I think it should equal, let's see, can you understand me? It should equal this, square root 5 over 2L, right? So we have VC2 will be omega times LPC2, so which will be omega times what? Square root 5 over 2L. See? We find all the centers C1, C2, and C3. We find all the absolute velocity of the three centers. Then we can use some expression to find the final. So I will erase all the things I just write on the screen, just for you guys to look at this. See, that's why, you know. Not that. So this VC1 equal half omega L, and VC3 here will equal this. And the last one, VC2, VC second equal this, right? And when we finish all the submembers of this whole mechanism, then we can use right. So here should because actually MOA, MAB, and MB also all value is M. So we have this, right? We have this. But you know, actually VC1, VC second, and VC third have different direction, which is here, here, and here. So it's better to project these three vectors into X, direction and y direction respectively, right? So we can find this is the final result. This is the final result. Can you guys understand the whole process of when we finish this example? So actually, I think its definition is very simple. It's just P equal sigma Pi, right? Equal sigma Mi VCI. So actually, we just need to know this definition. Then all the knowledge we should use is what we have learned from the middle part of this course, kinematics, right? We should from the information of point A to find all the other kinematic information of link AB and slider blocks B, right? So let me show you guys another example. Can you guys give me the result? So let's say if we have a wheel like this, let me tell you, it has a uniform omega, let's say equal 10 radians per second, and its R equal 5 meters. And can you tell me, let's see this wheel called C, right? We give it name C. So can you tell me its momentum PC equal what? So who can give me the answer? So you can just use the message. Tell me the answer is what? You can find the answer of this. Maybe I should give you guys this. The mass of the wheel is what? Let's see, just use 10 kilogram, right? So can you guys find its momentum PC equal what? Can you guys do the calculation? Does it calculate? Maybe I can give you another question. Let's see, but I need so you guys can think about this answer. If anyone who has the answer can just write on the message, right? Just tell me. Can anyone give me the answer?
Yes, Rasi.
So we have three problems. So let's see this another block called 1. So it had velocity with 10 meters per second, and its mass equal 10 kilogram. And how can you guys give me P1? How to calculate P1? What is momentum? We also have a rigid body OA. It has mass MOA equal 10 kilogram, its whole length LOA will equal 10 meters, and it has omega. So thank you, number 14, 5 Henry. So can you tell me which, so this is the second, and this is the third problem, this is the first. So, do you mean the first problem is answered is 5 Henry? Does anyone have different answer for the first question? Okay, I see your message. So Mr. Header said, 5 Henry, do you mean this? Do you mean PC equal 5 Henry? Does anyone have different answer for the first problem? Maybe I should record all the attendance of you guys. And then you can think about that. Let's see. I will first record all the attendance of you guys, and then wow, it's hard. What sound? Very interesting. Okay. Back to this page. Can you guess? Give the answer. Maybe I should change another color of my pen. Just use this purple color. So since no any gentleman gave me the answer, maybe we should talk about these three problems together, right? So once again, you tell me 500, right? So let's see together. Thank you for your sharing. So maybe we should once again to review the definition of the momentum of system of particles, right? So maybe I can write here, so it's momentum P will equal Pi, right? Like this, MI with I, right? So because back to this, so it's just one wheel, right? It's just one wheel. So we look at it is the radius body, so it kind of special case of a system of particles, a system of particles. So actually we should find its, first we should find its center of mass, you know? So it is a wheel with R equal 5 meters, but its center will always be here, you know? Its center of mass. Can you guys understand me? Its center of mass will always be here. Just it's, let's say it's O, right? So this point O, it always be its center of mass. So although we have omega with this 10 radians per second, and we have its mass with 10 kilogram, but its VO will always equal what? 0 meters per second. So actually for this wheel, HPC, because we give a name called C, so HPC should equal its mass times its VC. I'm sorry, actually this means it's center of mass. So here always equal 10 times 0, always equal 0. You know, always equal 0. Can you guys understand this problem? So just because it is a wheel, its center of mass will always be its rotation center. We know at a rigid body, when it has rotation moment, its rotation center will always have absolute velocity with 0, right? So the correct answer for this problem should be this one. So back to here, back to this. I think all you guys can find the correct answer for this, because you see, actually this block maybe in the rigid body one had a translational movement, then its center of mass will definitely equal 10 meters per second. So it P1 should equal mvc, right? Just equal 10 meters per second times 10 kilogram, right? It has 100. We should know its units. So the second problem is correct answer should be 100 kilogram meters per second. And for the third one, maybe I should iterate something to let you guys to see this clearly. Maybe I should just erase this, right? Just erase this. So we also use this, actually it's equal mvc, right? Equal mvc. So first we should find the center of mass of this OA. It's definitely in the half length of here. Here. So let's say this C is center of mass. So because the rotation in CW direction, so we just know its VC should along this direction. VC, right? And its magnitude should VC equal omega times half L, right? So we have 5 radians per second times what? Because the whole length is 10 meters, so here should be 5 meters. Then we will have 25 meters per second. Then we can find actually the momentum P equal m vc equal what? 10 kilogram times 25 meters per second. So the final result will be 250 kilogram. So can you guys understand the three problems? Can you guys understand that?
Oh, she.
Okay, okay. Okay, if you guys can totally understand the three problem. Actually, it is just a simple definition, right? It's just a simple definition. So first we should find the position of the center of mass, and the second we should find the absolute velocity of this center of mass. And the third we should use this. So if we just find just one body is momentum, it's quite easy, right? Like this, and this. But our task is to find the body system, maybe some mechanism. So maybe a little bit difficult for us is we should use some knowledge point we have learned from the kinematic part, especially for this AB, because it's a plane motion. To find VC second, VC3 is a little bit difficult. So anyway, I hope you guys can understand, and maybe you should do a little bit practice, right? Try to grasp all these knowledge points. So I think we can Maybe some gentleman just on the bus. You see, it's more like the voice from a bus, right? I just mute its voice. Okay, so let's continue. So I will continue to introduce the second concept. The second concept, we call that impulse. Impulse. So maybe some, especially women, I think, maybe Chinese, maybe another country's woman, all like to bet some things by impulse. Do you guys understand what I'm meaning? Because maybe you will pay a lot of money just to buy a lot of not very useful things just because of impulse, because you are attracted by some advertisement from the television or the website, although, so we call that 冲动, right? Impulse. But here we do not use impulse, 冲动, we use 冲击. So it's more like impact. So actually, we call that momentum in Chinese is 动量, right? So here we just talk about the second concept, impulse. In Chinese, we call that 冲量. So the product of a force and the action time of the force. So we can use that. It's more like F equal F times T, right? So that is 冲量. We call that 冲量. In English, we call that impulse. So so how can we understand this? So maybe I will give you a not good example, but maybe it helps us to understand this. So let's say it's our POW, right? I will just draw a very ugly POW. And we have a nail. Am I right? Nail, more like this. Oh, I have a needle. I try to push this into your palm and keep as long as possible the time. So maybe it's the force is I push this nail or needle into your palm. And the longer the time is, the painful you will feel is, right? So this time, this products of a force and it products to action time, right? Action time in Chinese we call it 作用时间, right? So this concept, we call that 冲量. In Chinese we call impulse. So impulse is used to characterize the accumulated effect on the body of a force acting during a certain time interval, right? So I think it's a little bit hard for me to give you very appropriate example in English, but in Chinese we have how to say that 成语 how idiom, I think we have 水滴石穿. Do you guys can understand me? I can tell you. So maybe it will describe a phenomenon that let's see. Let me show you guys. That is Chinese 成语 idiom. I think should idiom. Maybe I'm not correct in English expression. So let's say we have a rock. It's a kind of special material of rock. And maybe in some reason at this point, we'll always have some water drop. So 水滴 means water drop. Just like raindrop, right? It continued to to fall from this ceiling into the surface of this rock, maybe here. Because it always happened, maybe for years, right? So the final result is the water drop will finally like a hole, right? So maybe through some years, we will find actually this water drop will just through this rock into another position because it will have a hole in this rock. So because we know actually water drop can make a hole on some rock, it's impossible, right? But if time is long enough, it can happen. Actually, it's because the water and because the material of the rock, So maybe you guys can understand what I'm trying to talk about. Actually, show the force and its action time, the result, right? I think maybe there's some appropriate example in English, but I don't know that either. If you guys find one, you can tell me. So let's see. Once again, to read this sentence, impulse, we call that 冲量 in Chinese, is used to characterize the accumulated effect, 累积效果 accumulated effect on the body of a force acting during a certain time interval. So if a force is a constant vector, how to understand the constant? Means at different time, the moment, its magnitude and the direction will never change. So we call that it 常识量, right? It is 常识量. So we can always use this impulse just is this F times delta T. This is the time span from T second to T1. But if the force F is a variable vector, that means at different time moment, maybe its direction and magnitude will change from one value to another, from one direction to another. So this time we cannot do the product directly. So we should use element 原冲量. So we call that the element impulse means if we divided the time span into very short, let's say this time span from T1 to T second, but we just select a tiny length of in that delta T or dt, and let's see at this short time interval, its force will not change its magnitude and direction. So we have di, because that's the elementary impulse will just equal f dt, right? So the whole impulse from this time span from T1 to T second should use the integral calculation. So that means I should equal integral calculation from T1 to T second f dt, right? So this is the impulse concept. And we will continue to introduce this. It also can project to 3 axes, So because I also is a vector, right? We can get x, I, y, and I, z here. So you just need to have impression enough. It's not very important here. The impulse of a resultant force is equal to the geometric sum of the impulse of all component forces. So can you guys understand why we have this? The impulse of a resultant force is equal to the geometric sum of the impulse of all the component forces. Do you guys still remember the definition of a resultant force? The resultant force Fr means it equal sigma Fi, right? a lot of component forces, its geometric sum will be FR. Why we can use this FR replace this sigma Fi? Because it will have the same action to all these component forces. So through this, we also can find this, you know. So you can think we can do this. We can times dt and both together, and we can do the integral calculation together. Then we can find this, right? So that's the result. The impulse of resultant force is equal to the geometric sum of the impulse of all component forces. And the units of impulse is the same as the momentum, you know? So let's see, actually, the product of force times t time should be Newton times S. But we have second law of Newton's. We have F equal ma, and this is kilogram times meters per square per second square, right? So that means n also equal this. So we can use this kilo squared to replace n, and then times s. Then it will change into kilogram meters per second. So that's why the unit of impulse is the same of that momentum. You know, so this is 动量, this is impulse, this is impulse. Let's continue. Then we are going to move the third part. That's the core, you know. This is the core of chapter 12. It will talk about theorem of momentum, but today we don't have enough time to finish the whole section. So let's see the first theorem of momentum for one particle. Do you guys still remember what I have mentioned? Logical path. See, once again, first it tells us theorem of momentum for one particle, right? Because what? Because we have this. This is second law of Newton's. You know, I think all you guys will know the second law of Newton. And for one particle, all the forces acting on this particle will always constitute a concurrent force system, which means we always have a resultant force Fr equal all the force acting on the same particle, right? So according to the second law of Newton, we will always have this, you know? So ma is acceleration of this particle, so it will dv dt. So this a will equal dv dt, because once again, we think about m will never change at different time moments. So we can use this, you know? So we can do this. So dmv dt, actually it equal ma. And we have the definition mv means p, right? So that is so-called theorem of momentum for one particle. So the derivative of momentum of a particle with respect to time is equal to the force acting on the particle. You know, actually, when we are talking about the theorem of the momentum for one particle, it's meaningless. Actually, if we stay here, we stop here, we just talk about the so-called theorem of momentum for one particle, it's meaningless. Why it's meaningless? Because actually it is ma equal L, right? Actually, it just do some change from here to here. Actually, it's the same, right? So let's see. But we have our logical path, you know. First, we are talking about theorem of moment for one particle. Then we'll finally to talk about for particles of system, right? We have our logical path, right? From simple to the complicated situations. So let's see. We have differential form. So dmv equal f dt dx, right? So we can change this again. So we just use this dt to the right part of this equal sign. So we have dmv equal f dt, right? So that's why we have these two definitions first. This is p, and this is I impulse, right? So the differential of the momentum of a particle equal the elementary impulse of the force acting on it, right? And we also have, actually in China we call it differential formula, 微分形式, right? 微分形式. And we have integral form, that is 积分形式. So since we have the differential form, so we can from t1 to t2 do the integral calculation from this. So we have, when we do this, so the left part of this will change into this. Actually, it means the change of its momentum, right? It's the change of its momentum. So that in a certain time interval or time span, right? Or time span, the change of the momentum of a particle is equal to the impulse of the force during the same integral of time. So maybe I will repeat that again. In a certain time interval, the change of momentum of a particle is equal to the impulse of the force during the same interval of time. So you guys just have a basic impression of this is enough, because our main focus will be theorem of momentum of particles, system of particles. We should use these basic things to deduce the final result of the system of particles. Let's see. Let's continue. And for one particle, we also can have this projection form, right? Projection form, we can have this. dmvds, you know, we can I can rechange it m dvx dt actually is ax. See? It is the second law of Newton's, right? It's just to change into this form to show get that x is p, so it can write as dpx dt equal fx, right? And here we can write dpy dt equal fy. So if we have a rigid body which has the translational moment, because every 2 points on the same body will always have the same velocity and same acceleration, right? So we can just treat this rigid body as a single particle is enough, right? So we can use this maybe to find its relationship between the acceleration and f, right? So we have this form and also this form, but I think it's not very useful, because for a single point, for a single particle, a Newton's second law is enough. We just use this is enough, right? So let's say we have pulley, and which draw this MA to have this A. So how can you find its FT? So we just select it as the object, so it has FT. It has its right, its weight. So we can just use second of law, so sigma f will equal ft minus mag, which equal ma, right? We do not need this for just one particle. but this is prepared for us to change this one particle into a system of particles, 质点系, right? Or 质点系. So maybe next time we are going to talk about of the particles. So the final part is the law of conservation of a linear momentum of particle. Let's see. So if F equals 0, right? If F equals 0 means this P will be a constant vector, you know? So then MV is constant. Why it should be constant? Because we have dp dt equal F equals 0. That means it will be a constant vector. So that means then MV is a constant vector and the particle is then inertial motion. So actually it's in the state of equilibrium, you know? So inertial motion means 惯性运动. So if a particle is in the state of equilibrium, it always keep its original movement. So there's only two capable of movement. One is stationary, 静止, stationary. Another is the uniform velocity along some line, 匀速直线运动, right? So that's the so-called inertial motion. And if only at some direction is true, so if we only have fx equals 0, then because we have dpx dt equal fx, so this means px will be a constant vector. It will tell us then mvx is constant, and the motion of the particle along axis is an inertial motion, right? 惯性运动 also means that sigma fx always equals 0 at x direction is in the state of equilibrium. So maybe we will use this condition to find some solution of some given problems. So let's see, we also have this integral expression. We also have this, right? So mv second x equal mv 1x equal mvx equal 0, right? Equal some constant value. Next time we'll start to talk about theorem of momentum of system of particles, 质点系的动量定理. So if you guys have time, I hope you guys can read the textbook of this part before our next time's class begin. And I think that's all for today. We don't have homework today, so I think it's time to say goodbye to all you guys. I hope all you guys had a wonderful day. Okay, bye bye.
OK，拜老师。
下
各位老
课，
师，拜，
拜拜，
再见。
再见，下课了，拜拜。
拜拜，老师，拜拜。